For these notes, we're going to be talking about elastic collision in one dimension. Okay, so um, for this part, we're going to be using both laws of conservation of energy and conservation of momentum in order to come up with the equations. So the law of conservation of motion, when we expand it out, okay, so we have the initial momentum of the first object, the initial momentum of the second object, right, is set equal to the final momentum of the first object and the final momentum of the final object, all added together, right? And then that's just expanded out to our m times velocity, mass times velocity. Okay, for the law of conservation of energy, we have each of the energies, the kinetic energies for the initial and final of each object. Okay, and so these notes kind of just goes through the way that we can blend them together, so deriving them into the equations that we need. The key ones that we just need to focus on, or you need to focus on for your homework, is this one that I have highlighted here, that the initial velocity of the first object plus the final velocity of the first object is equal to the final velocity of the second object plus the initial velocity of the second object. Okay, this is a kind of shortcut equation that we can use, and I'll kind of show you in one of the examples how we can use it and save yourself a little bit of time in calculations. Okay. Then they go on to derive the other two for V1F and V2F. So here we have the equation that has been rearranged to solve for the final velocity of the first object, and then this one is for the final velocity of the second object. Okay, so those three equations that I've kind of highlighted here in our notes are the ones that we're going to be using. So there's no actual example problems, but I am just going to go over question 4 with you guys as kind of our practice. Right, so we have an alpha particle that's traveling 1500 meters per second north and collides with a proton traveling 1800 meters per second south. Determine the final velocities of both particles after this elastic collision. Okay, you'll notice that I first determined what my directions are. So north is going to be positive, south is going to be negative. I then went through and just wrote out what variables they gave me in the problem. So for my alpha particle, I put down the mass. Okay, my initial velocity was going to be the positive direction because it was going north, so 1500 meters per second. Okay, compared to my proton, I put my proton mass. I also put down my velocity, my initial velocity of my proton. Because it is moving south, it is negative. Okay, so first I'm just going to solve for my alpha particle, which is I'm going to call the first object. So here I have the equation written out for finding the velocity, the final velocity of my alpha particle. So when I plug in the information, I'm going to have VAF is equal to 2, my mass of my proton, so 1.67 times 10 to the negative 27th, times my velocity of my proton, so negative 180, or negative 1,800 meters per second, plus my mass of my alpha particle, so 6.64 times 10 to the negative 27th, minus the mass of the proton, times the initial velocity of my alpha particle, so 1500, all over mass of my alpha, so 6.64 times 10 to the negative 27th, plus the mass of the proton, 1.67 times 10 to the negative 27th. Right, so whenever I go through and solve for VAF, I get that my VAF is equal to 173.65 meters per second. Okay, So I found VAF. Now I need to find VPF, the final velocity of my second object, which in this case is the proton. Okay, so I could go back and use the other equation that is derived at the bottom of the notes to solve for the final one. But like I said, we can use this equation as a shortcut because now we know 3 of the 4 variables for this equation. And it is a much simpler equation to go in and plug in the information. So for this, I have my VAI, which was 1500, plus my VAF, which is what we just calculated, 173.65, is equal to my VPI, which is negative 180 or negative 1800, plus my VPF, which is what I'm trying to calculate for. Okay, so whenever I solve for VPF, I will get that my VPF is equal to 3473.65 meters per second. Okay, so you will notice that it is a positive velocity, so it will be headed in the north direction now. Okay, so if you would have went back and plugged in all the information, but for the for finding the velocity, final velocity of the proton, you would have gotten the same answer there as well. I do just want to talk about question 3. So it says 2 carts in a frictionless track have a mass of m and 4m respectively. And so here I've labeled this will be my first object, this will be my second object. The heavier the cart is traveling, or the heavier cart is traveling 0.78 meters per second east. The less massive cart is traveling 1.3 meters per second west. After a head-on collision, elastic collision, determine the final velocities of both carts. Okay, so the key thing with this, because we do have, we still kind of have variables as far as our mass goes. Our mass of 1 is going to be m. Okay, our mass of 2 is 4m. So those will be the things that we plug into our formulas. And then you'll find that the m's are actually going to cancel because you'll have an m on the numerator and an m in the denominator that will cancel out. Okay, so I just wanted to address that. So you'll be doing questions 1 through 3 for that section. Moving on to elastic collisions in 1D, there are very special cases. So the first special case that we're going to discuss is the second mass is initially stationary. Okay, so if the second object's initial velocity is 0, then these equations are going to simplify from this to this. Okay, or these are 2 different ones. So we have these 2 that are simplified from the previous ones that we were using. The second special case is that the second mass is very large. Okay, so for this, we basically consider the first mass to have a mass of 0 since the second one is so large. Okay, so in this case, if we plug in 0 as our masses for the first object, we find that the velocity of, or the final velocity of the first object is going to equal the final, or the initial velocity just in the opposite direction. So the negative velocity of the initial first object. Okay, so think of this if we had a wall that had a very large mass, and if we threw a ball at the wall, okay, when it collides with the wall, the velocity at which it collides with the wall, we would expect that it would bounce with the same amount of velocity back in the opposite direction, and then the wall would not move at all. Its velocity would not change at all. And then special case number 3, if we have 2 identical masses, we would replace our m1 and m2 with just m. So it would simplify down into these 2 equations. So the final velocity of the first object is going to equal the initial velocity of the second object, okay? And the final velocity of the second object is going to equal the initial velocity of the first object, okay? So they're basically passing on the momentum to each other. For each of the practice problems, you're just going to practice problems questions 1, 2, and 3. They do follow the special cases respectively. So question 1 is you're going to be using the equations for the special case number 1. For question 2, special case number 2. Same for question number 3. I do just want to talk about question number 3. So it says after a head-on elastic collision between two curling rocks of equal mass, the initially stationary second curling rock travels 1.9 meters on the ice. It gives us a coefficient of friction before stopping. Determine the initial speed of the first rock. Okay, so I started out by just writing in what variables we knew. So we knew that the distance that the second object traveled was 1.9 meters. Okay, we knew that the initial velocity, the final velocity, sorry, because it said it travels before stopping. So the final velocity is going to be 0. So we need to know what the initial velocity is of the rock when it collides. Okay, and so what we need to do is we do need to use kinematics for this. So using the information that we know, if we have our curling rock here, we know that force of gravity is pulling down upon it. The normal force is pushing up on it. The rock is not falling through the ice, so they're going to be equal, but in the opposite direction. Okay, so remember that the force of friction is equal to our coefficient of friction times the normal force. So if we plug in what we know for normal force, it's going to be the positive of our mass times gravity. So we have mu times mass times gravity. And then for force of friction, remember all force is just mass times acceleration. So I put in my mass times acceleration. My masses are going to cancel, so I'm left with acceleration is equal to mu times gravity. Okay, I did write out the kinematic equation that you're going to need, just so you didn't have to go back through your notes. So you'll plug in the information that we have. So we have our V2, so you would plug that in here. V1 is what we're solving for. 2 times acceleration, you'll plug in your mu times gravity. You can plug in that information here and get the actual number before you plug it in, because we have the mu and we know what gravity's constant is. And then you're going to plug in your displacement.